Hello there. Have you ever wondered about the orbit of the Earth? Well, it's not a circle, but an ovaloid shape called an ellipse, and we can model it in a periodical graph to find our distance from the Sun during a certain day. Let's put it this way. Earth's orbit around the Sun is in this shape called an ellipse. It is shaped like an oval, and our dear old planet hits 2 points during its revolution around the Sun called the aphelion and the perihelion, where the perihelion is the closest point to the Sun and the aphelion is the farthest point to the Sun during our revolution. Now, this does not mean our orbit is irregular, far from it, where its distance from the Sun is periodic, which means we have repeating patterns of distance from the Sun during, well, our orbit. And that is how we can find the distance from the Sun during specific days, no matter the number of years down the line we want to find. Right, so now that we have understood how the Earth revolves around the Sun and why it's periodic, we can now graph this behavior and prove its periodicity. I have my Jupyter notebook open and I have the NumPy and Matplotlib packages imported. And for those of you who want to do this yourself but do not have any Python experience, I recommend doing a Python tutorial and then a NumPy tutorial for Jupyter notebooks. Now, I'm probably going to speed up what I'm doing here, but what I'm basically going to do is just script and then I'll explain what I'm doing. Right, so now that I've actually written the script, I'm going to quickly explain what's going on here. So we've set the average distance as 149.6, where the perihelion is 147.1 kilometers away from the sun, and the aphelion is 152.1 kilometers away from the sun. The average distance of this would be 149.6 kilometers away from the sun. We set the variation, or in the case of a sine graph, the amplitude as 2.5 or 2.5 kilometers in terms of our distance. This would mean it's plus or minus 2.5 kilometers for this zero, in this case, of our graph, 149.6 kilometers. Then we return all of this and multiply it into np.sine, and we multiply 2 into pi and divide it by 365 to get the sine graph, and then finally multiply this into the days. We set this days as np.linspace 0, 365 into 3, and we make 3000 points. The 0 is obviously the starting point of the graph, and then the 365 into 3 is just making 3 loops to make sure that the graph actually looks like a sine graph, and we can see the periodicity. If we set this as just 365, then we would only see one period rather than, let's say, multiple periods, and we do this into 3 to make 3 periods. This would be our x-axis. The distance itself is technically our y-axis, and this is the Earth distance, days, and this is our function itself. Now let's try running this. There we go. Now we can see that this graph looks quote-unquote periodic, or it has repeating patterns between every 365 days. Now let's say we set this as just 365 days. We would see that this is one period of the graph, and you could say that this has no repeating pattern. Now that's why we would do this into 3. That means we would have this distance for every 3 years, and we can see that there's exactly 3 patterns of this one period repeating. So we would say that this graph is periodic. Right, now to actually prove that this graph itself is periodic, I'm going to add a few lines of code that checks the distance from the Earth during specific points of the day. Alright, so let me quickly explain what I've done here. I've taken a specific day in the graph, here let's say day 100, and I wanted to find out what the distance of the Earth is during the specific day. Then I wanted to do this the same way but for the next year or the next period. So I've just added another 365 days to complete this cycle or period for the first period, I guess. And then what I've done is get the distance for this day as well. And theoretically, if the graph is periodic and the distance is the same, so that means this graph is periodic and the distance of the Earth from the Sun during these days would be the same.